In today's lecture, I'm going to talk about directional derivatives of convex functions and their relations with subgradants of convex function. Let me give the definition of the directional derivative of a convex function. Definition. Let f from Rn to the extended real line be a function and let x bar be a point in the domain of the function. Okay, the directional derivative of f at x bar in the direction d is given by the following formula. The directional derivative of f at x bar in the direction d is the limit of f of x bar plus td minus f of x bar over t. Here t approaches 0 from the right. If this limit exists, and to clarify, I want to mention that if this limit exists as a real number, or plus or minus infinity. Okay, so later on we're gonna see some examples where the directional derivative could be plus or minus infinity, and we will show that for a convex function the directional derivative at x bar in the direction d always exists. Okay, and similarly we can also define the left directional derivative at x bar in the direction d by the following formula: f prime x bar d. Over here we put the minus sign to specify the left derivative, so it's the limit where t approaches 0 from the left of f of x bar plus td minus f of x bar over t. Okay, so and as we can see, the left directional derivative can be represented in terms of the directional derivative. Therefore, later on we will deal mostly with the directional derivative of f at x bar in the direction d. So from the definition, we have the following relation: the left directional derivative of f at x bar in the direction d is equal to minus of the directional derivative of x bar of f at x bar in the direction minus d. Okay, so how come this is true? We can easily prove this from the definition. Okay, so by the definition I can write like this: the left directional derivative of f at x bar in the direction d is equal to the limit of f here x bar plus t times d minus f of x bar over t, where t approaches 0 from the left. Okay, So it is equal to the limit of f of x bar plus minus t times minus d minus f of x bar. Here we divide by minus t, where t approaches 0 from the left. But in order to make sure that the equality is valid, we need to put a minus sign over here, okay? To make sure that minus t is just t, and here minus t times minus d is the same as t times d, okay? So this is the same as minus lim as t approaches 0 from the right of f of x bar plus s times minus d minus f of x bar over s. Here s approaches 0 from the right. We obtain this by a very simple substitution. We let s by minus t, okay? So this is just minus the directional derivative of f at x bar in the direction minus d by the definition. Our next goal is to show that for a convex function, the directional derivative at any x bar in the domain of the function in any direction d exists. In order to achieve the goal, let me introduce an important lemma. Let f from Rn to the extended real line be a convex function. And let x bar be a point in the domain of the function, and let d be a vector in Rn. Define the function. Phi of t is equal to f of x bar plus t times d minus f of x bar over t. Here t is positive. In this way, we have defined a function phi that goes from the open interval 0 to infinity to the extended real line. Okay, the conclusion is then phi is non-decreasing on 0 to infinity. Okay, so to see the behavior of the function phi, let's look at a graph. So this is the graph of a convex function on the real line, and this is x bar. For example, if we take d equals 1, then this is x bar plus t times d, okay, where t is positive. Now, then phi of t is f of x bar plus td minus f of x bar divided by t, and remember that here d is equal to 1. So phi of t is actually the slope of the secant line connecting this point and this point. And as you can see from here, if t is larger and larger, the slope of this tangent line is also larger and larger, and therefore phi is a non-decreasing function. Let me go ahead and give the detailed proof. This is x bar. This is x bar plus t1 times d, and this is x bar plus t2 times t, where 0 is less than t1 and less than t2. Okay, so in order to complete the proof, I'm going to take any t1 and t2 in the interval 0 to infinity with t1 strictly less than t2. Okay, then from this figure we see that t x bar plus t1d belongs to the interval connecting x bar and x bar plus t2d. Therefore, x bar plus t1d can be represented as a convex combination of x bar and x bar plus t2d. How can we have that representation? Let us write in this way: x bar plus t1 times d is equal to, over here we write x bar plus t2 times d, and we multiply by t1 over t2, which is a number in between 0 and 1. Okay, so after this multiplication, we see that over here we obtain t1 over t2 times x bar plus t1 over t2 times t2d, which is d. Okay, so to make sure that the equality is valid, we add this by 1 minus t1 over t2 times x bar. Okay, so let me double check. This is t1 over t2 times x bar. This is 1 minus t1 over t2 times x bar. So we have x bar. And now here, this is t1 over t2 times t2d. So we have t1d. Therefore, this equality holds. Now, because this is a number in between 0 and 1, okay, then this is actually a convex combination of x bar plus t2d and x bar. Okay, by the convexity of f, we have the following inequality: f of x bar plus t1 times d is equal to f of t1 over t2 times x bar plus t2 times d minus plus 1 minus t1 over t2 times x bar. Okay, this is less than or equal to t1 over t2 times f of x bar plus t2 times d plus 1 minus t1 over t2 times f of x bar. In the next step, I'm going to subtract f of x bar from both sides. So from here, if we subtract f of x bar from both sides, we have this: f of x bar plus t1d minus f of x bar is less than or equal to t1 over t2 times f of x bar plus t2 times d minus, because we subtract f of x bar from this, we have t1 over t2 times f of x bar. Okay, now in the next step, I'm going to divide both sides of this inequality by t1 and obtain the following inequality: f of x bar plus t1 times d minus f of x bar over t1 is less than or equal to f of x bar plus t2 times d minus, because we divide by t1, then t1 disappear over here. So here we have f of x bar plus t2 times d minus f of x bar over t2. Okay? And this is actually 5 of t1. And this is 5 of t2. So we have showed that if t1 is less than t2, then 5 of t1 is less than or equal to 5 of t2. Therefore, 5 is non-decreasing on the interval 0 to infinity. And the proof is complete. Now I'm ready to show that for a convex function, the directional derivative always exists. Let f from Rn to the extended real line be a convex function. And let x bar be a point in the domain of the function. Then the directional derivative f prime of x bar in the direction d exists for every direction d in Rn. In addition, if x bar belongs to the interior of the domain of the function, then the directional derivative of f at x bar in the direction d is a real number. For every d in Rn. Okay? So let me give the detailed proof of this proposition. Now, here we use the representation of the function 5 given in the previous lemma. So 5t is equal to f of x bar plus t times d minus f of x bar over t. Okay, and t is positive. By the definition, f prime of x bar in the direction d is equal to the limit as t approaches 0 from the right of f of x bar plus t times d minus f of x bar over t. Okay, and this is just the limit as t approaches 0 from the right of 5 of t. And as proved from the previous lemma, 5 is a non-decreasing function. Therefore, this limit always exists as an extended real number. And in fact, it has this representation. It's the infimum of 5 of t, where t is greater than 0. Okay. Since 5 is non-decreasing, f prime of x bar in the direction d exists as a real number or plus or minus infinity. Okay. Now, under this additional assumption, that is, x bar is in the interior of the domain of the function, we're going to show that f prime of x bar in the direction d is always a real number. Okay. Before, we proved a very important property of a convex function. That is, if x bar is in the interior of the domain of a convex function f, then f is always locally Lipschitz continuous around x bar. Okay, and we're gonna take advantage of that property in order to prove this proposition. Okay, because x bar belongs to the interior of the domain of the function f. The function f is locally Lipschitz continuous around x bar. Okay. Thus, there exists L greater than or equal to 0 and delta greater than 0 such that the absolute value of f of x minus f of y is less than or equal to L times norm of x minus y whenever x and y are in the ball with center at x bar and radius delta. Okay. So then we obtain the following: the absolute value of f of x bar plus t times d minus f of x bar is less than or equal to L times t times norm of d for small t greater than 0. Okay. How come this is true? Because for t sufficiently small, x bar plus t times d belongs to the ball with center at x bar and radius delta. And obviously, x bar is in this ball. Okay, so then we can obtain this inequality by applying this inequality where x is equal to x bar plus t times d and y is equal to x bar. Okay, so from that inequality we get the absolute value of f of x bar plus t times d minus f of x bar over t is less than or equal to L times norm of d for small t greater than 0. Okay, and as we know, the limit of f of x bar plus td minus f of x bar over t as t approaches 0 from the right always exists. And from this inequality, we see that the limit has to be a real number. And in fact, that real number is always less than or equal to L times the norm of d. Okay, so taking the limit as t approaches 0 from the right, we get that the absolute value of f prime at x bar in the direction d is always less than or equal to L times norm of d. Therefore, the directional derivative at x bar in the direction D is a real number, and the proof is complete. Our next goal is to establish the relation between the directional derivative of a convex function and its subgradients. The following lemma is very simple but important for what follows. Let f from Rn to the extended real line be a convex function, and let x bar be a point in the domain of the function. Then the directional derivative of f at x bar in any direction D is always less than or equal to f of x bar plus D minus f of x bar, and this is true for all D in Rn. Okay, the proof of this lemma is very simple. As we know, the function five t given by the function 5 given by 5t is equal to f of x bar plus t times d minus f of x bar over t is non-decreasing on the interval 0 to infinity. Okay, thus 5 of t is always less than or equal to 5 of 1, and 5 of 1 is equal to f of x bar plus d minus f of x bar, and this is true for all t in the interval 0, 1. Okay, how come this is true? It is very simple, because t is less than 1, so 5t is less than or equal to 5 of 1, as 5 is non-decreasing. And what is 5 of 1? 5 of 1, we only need to replace t by 1 in this representation. So 5 of 1 is equal to f of x bar plus 1 times d, so it's just d, minus f of x bar over 1. And so we obtain this, okay, by the definition. The directional derivative of f at x bar in the direction D is the limit as t approaches 0 from the right of 5 of t as seen from the previous proof. And therefore, this is always, this is the same as the infimum of 5 of t as t greater than 0. So this is obviously less than or equal to 5 of 1, which is f of x bar plus d minus f of x bar. Okay, therefore the proof is complete. The next theorem gives a very important representation of the subdifferential of a convex function in terms of its directional derivatives. Let f from Rn to the extended real line be a convex function, and let x bar be a point in the domain of the function. The following properties are equivalent. The first property is V belongs to the subdifferential of f at x bar. The second property is the inner product of V and D is always less than or equal to the directional derivative of f at x bar in the direction D for all D in Rn. And the third property is the directional derivative, the left directional derivative of f at x bar in the direction D is less than or equal to the inner product of V and D, and is less than or equal to the directional derivative of f at x bar in the direction D for all D in Rn. Okay, so I'm going to go ahead and give the detailed proof of this theorem, but before giving the proof, let us discuss a very important consequence of this result. In fact, from this theorem, we can represent the subdifferential of a convex function f in terms of its directional derivative by the following formula. So, from the equivalence of I and double I, we have that the subdifferential of f at x bar can be written as the set of all V in Rn such that the inner product of V and D is always less than or equal to f prime of x bar D, and this is true for all D in Rn. Okay, so this nice representation allows us to write the subdifferential of the function f at x bar in terms of its directional derivative, or we can use the directional derivative to characterize subdifferential of convex functions. Okay, and from this suggests a way to study subdifferential of convex function. We can first study directional derivatives of convex function, and then use directional derivatives to study properties of subdifferential of convex functions. Okay, now I'm going to go ahead and give the detailed proof of this theorem. Now I'm going to go ahead and prove the theorem. Let me start by proving the first property implies the second property. So we fix any V in the subdifferential of f at x bar. Then, by the definition of the subdifferential, the inner product of V and x minus x bar is always less than or equal to f of x minus f of x bar, and this is true for all x in Rn. Okay. Now, let us apply this inequality where x is replaced by x bar plus t times t. Okay. Then the inner product of V, and over here we have x bar plus t times t minus x bar is always less than or equal to f of x bar plus t times t minus f of x bar. Okay, and this is true for all t greater than 0 and d is in Rn. Okay, then we simplify this inequality and obtain the inner product of V times t d is less than or equal to f of x bar plus t times t minus f of x bar. Okay, and by dividing this both sides of this inequality by t, we obtain this: the inner product of V and d is less than or equal to f of x bar plus t times t minus f of x bar over t. And remember that this is true for all t greater than 0 and for all d in Rn. Okay. Now, because this is true for all t greater than 0, letting t approaches 0 from the right, we obtain the next result. Letting t approach 0 from the right gives the inner product v and d is less than or equal to the directional derivative of f at x bar in the direction d. And this is true for all d in Rn. Okay, so we have completed the proof that the first property implies the second property. Now let us show that the second property implies the first property. Here we suppose that the inner product of v and d is less than or equal to the directional derivative of f at x bar in the direction d, and this is true for all d in Rn. Okay, by the previous lemma, the inner product of v and d is less than or equal to the directional derivative of f at x bar in the direction d, and this is less than or equal to f of x bar plus d minus f of x bar. And this is true for all d in Rn. Okay, so from this we get that the inner product of v and d is less than or equal to f of x bar plus d minus f of x bar, and this is true for all d in Rn. Okay, if we look closely at the definition of the subdifferential of the a convex function at x bar, we see that therefore v is in the subdifferential of f at x bar. Okay, so we have completed the equivalence, the proof of the equivalence of the first property and the second property. Now let me go ahead and show that the second property is equivalent to the third property. This implication is obvious. Now why? Because if we assume that this is true, the third property is true for all d in Rn. In particular, the second inequality here is true for all d in Rn, and that is actually the second property. So there is no need of further proof in this situation. Okay, so to complete the proof of the theorem, we only need to prove the implication double I implies triple I. So here we suppose that the inner product of v and d is less than or equal to the right directional derivative of f at x bar in the direction d, and this is true for all d in Rn. So because this is true for all d in Rn, then it is true for minus d for whatever d in Rn. So the inner product of v and minus d is less than or equal to the directional derivative of f at x bar in the direction minus d for all d in Rn. Okay, then minus of the directional derivative of f at x bar in the direction minus d is less than or equal to the inner product of v and d for all d in Rn. If we remember the relation between the left directional derivative of a function at x bar in a direction, then we will see that from here the left directional derivative of f at x bar in the direction d, which is the same as this, is less than or equal to the inner product of v and d for all D in Rn. Okay, so if we combine this and this inequality, we see that the third property is satisfied. Therefore, the third property is satisfied. Therefore, we have completed the proof of the theorem.